Hello class, welcome back. Today we're going to be going over chapter 11, which talks about light and electromagnetic waves. Well, light is an electromagnetic wave. So, in this lecture, again, I'm going to be going through the PowerPoint, and I'm going to be talking about the electromagnetic spectrum, or basically the light spectrum, transparent and opaque materials, reflection, refraction, color, dispersion, and polarization. All right. So, getting right into it, we know light is basically a electromagnetic wave. So basically, if you induce a electric and magnetic field, then you're basically producing light. And so these two words are basically like interchangeable. If you have an electromagnetic wave, then you basically have light. If you have light, then you have an electromagnetic wave. And light is basically created, or electromagnetic waves are created by vibrating electric charges. And let me give you the speed of this wave. It's basically the speed of light, or the speed of electromagnetic waves. So we use C for the speed of light, and it's going to be equal to 3, basically 3 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros, meters per second. So this is how fast light is, or this is how fast all electromagnetic waves travel. And we can basically abbreviate this by just saying, well, it's 3 times 10 to the 8 meters per second. Speed of light, basically only light can go at this speed. Nothing can go any faster than this. This is basically the speed limit of the whole universe. Nothing can go faster than this speed here. So let me kind of describe light waves and sound waves and kind of how they differ. So we know sound waves, for the speed of sound, so Vs, values for the speed of sound, was 340 meters per second. So kind of the main difference the difference that I want to point out here is that sound needs a medium to travel through. So sound needs a medium to travel through. So that medium could be like air, water, steel, something, some type of medium. Sound needs some type of medium to basically travel in. So sound won't be able to travel in space or in a vacuum because there is no medium. It's just a vacuum. There's nothingness out there. Well, light, which is an electromagnetic wave, does not need a medium. So light, that sucks. So light does not need a medium. So light does not need a medium to basically travel. Light can travel in space, which is a vacuum. It can travel in air, water, metal. Light can basically travel through anything. Whereas sound actually needs a medium. So just want to point out that difference. And another thing about light is that I want to point out is light is a transverse wave. Is a transverse wave. Boom. And what is a transverse wave again? Well, a transverse wave is, when you hear the word trans, you can think of across, because trans means to go across something. So basically a transverse wave is something that's kind of going up and down but the wave's going this way like that. So this is kind of like a jump rope. So if you take a jump rope up and down, the wave goes basically to the left or the right of your up and down motion. So this is, again, a transverse wave. So all light are transverse waves. Or basically light is a mixture of electric and magnetic fields, basically, that kind of alternate between each other. So if you would imagine this black line as the electric field, then the magnetic field would be going kind of like that. So you can kind of imagine the electric field going up and down, and the magnetic field going in and out, kind of. So it's the combination of both of those waves that basically produces light, and both of those are transverse waves. Okay. So now, let's talk about the electromagnetic spectrum. So, basically light, it has a whole spectrum of basically wavelengths and frequencies. So the different wavelengths and frequencies of light are what we call the electromagnetic spectrum. So let's say down here is, let's say it's about 10 to the 3 meters. I'm gonna write it like this so you kind of see the difference. So this is basically 10, 1, 2, 3 meters. So this is really, really long. Actually, yeah, this is really long. And then down over here, we have 0.12341 meters. So you can imagine this top as the wavelength. So the wavelength of a wave, where the wavelength, remember, was this here. So the distance from there to there is one wavelength. So you can imagine this wavelength as, 10,000, or this wavelength being really, really small, so 0.0001. So that's like the whole range of light there. And of course it goes on in both directions, but this is the main spectrum here. So let me make some marks. So let's say around right here is 1 meter. Around here, oops, it's actually way smaller. That's 1 meter. Let's say right here is 10 to the 6 nanometers. Right here, 10 to the 3 nanometers. Right here, 1 nanometer. And over here, 10 to the negative 5 nanometers. And a nanometer, write it right here. So nm is for nanometer, and nanometer basically just means 10 to the negative 9 meters. So it's basically 9 zeros in front. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then a 1 is basically like a nanometer. 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be like right here. Boom. So this here is 1 nanometer. So again, kind of imagine how small that basically is. All these zeros and then a 1 is 1 nanometer. So here, 1 meter, this is 10 to the 6 nanometers, 10 to the 3 nanometers, 1 nanometer. So this value is right here, and then it just gets smaller and smaller from there. And again, these are wavelengths that we're talking about. Okay, so right around this region, kind of right around this region, is where we have visible light. Visible light. Well, this is basically light that we can see with our eyes. So if you're looking at the PowerPoint, I'm looking at slide number 5. The image drawn there is a lot more clear than what I have here, but it's along these lines. So here in this small region is the visible light range. So this is all that we can see with our bare eyes. So the red, blue, pink, greens, all those colors in between, they all fall under this small range here. And then going in this direction, so let's say we have basically red on the bottom end. We have red towards the bottom end. And we have blue up here on the upper end. And so as the wavelength gets bigger, then we get into the infrared region. So about right here, from here to here, is roughly about the infrared region. And infrared is basically heat, well not heat, but it's basically temperature. Because your body gives off a certain amount of body heat, right? And that body heat can be seen with infrared goggles or night vision goggles. So basically your body is giving off light or electromagnetic waves in the form of heat in the infrared region. But we can't see it. But let's say you could see into the infrared region, then you would be able to see basically how hot a person is. So if a person is really, really cold, you would be able to see that because they would be somewhere in the infrared region. So there's infrared, and then as the wavelength gets bigger and bigger, we have microwaves. So I'm write that right here. Microwaves, which is what we use to basically warm up our food. And then down here, these really, really big waves are radio waves. And so you can see these radio waves have very, very long wavelengths, up to the tens of thousands. And so that's because radio waves have to travel long distances, all over the earth. Radio waves is how we communicate through cell phone towers, broadcasting signals, etc., all that. So all those kind of waves have to travel long distances, which is why radio waves have these long wavelengths. So now going back the other way, so we have radio waves, microwaves, infrared waves. So wavelengths getting shorter and shorter. Now going this other way, after the blue, we have basically ultraviolet. And so ultraviolet light is basically the light that's given off by the sun. So we have ultraviolet, ultraviolet. Then we have X-rays, and gamma. Just hope you can see that, gamma rays. So as the wavelength gets smaller and smaller and smaller, we get into the ultraviolet, the X-rays, and the gamma rays. And so these wavelengths are really, 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 really small. So these wavelengths are harmful to the human body if you're exposed to it at a high dose. So of course, if you're exposed to a high dose of ultraviolet or just a good amount of the sun, you can get skin cancer. If you're exposed too much to X-rays, you can also get a form of cancer because these waves are so small, they can basically get in our skin, through our skin, into our cells, and cause cellular damage. And then of course, gamma rays, which are even smaller, can reach even deeper into our body and cause internal damage on the cellular level. because these waves are so small. So that there basically is the whole electromagnetic spectrum. And then here is the small region that we can see. And then of course we use these other areas of light for different things. So microwaves for heating up things, radio waves for communication, X-rays for medical techniques, and even gamma rays, I think sometimes for like radiation therapy or something like that. Okay. So I guess the last thing I want to say about this is, as the wavelength decreases, the frequency is going to increase, right? So let me write that. So as it goes this way, frequency increases. And that makes sense, right? Because you have this long wave. It's so long that it's not very, it's not very frequent. But if it's a really short wavelength, then the frequency can be, really fast. So as you decrease the wavelength, you're basically increasing the frequency. So let me kind of show that with the equation. So we know the speed of light. Well, from the previous video, we know speed is related to the wavelength times the frequency, right? So since all light travels at the speed of light, we can just say, well, this equals c, right? Well, this c is not going to change. It's going to be constant. That stays the same. So that means these two are interchangeable. So then, if the frequency goes up, well, let me say this, if the wavelength goes up, then the frequency has to go down, because if you increase the wavelength, the frequency has to decrease in order to balance out and keep that same speed. And same vice versa, if the wavelength decreases, then the frequency must increase. Boom. And that's if, this is all while in the same medium. So same medium. And so if light travels in a different medium, then it will travel at a different speed. But when light is in air or in space, it travels at the speed of light. So light travels at this speed here in air, or in a vacuum. But we're going to get into later what happens when light travels through different mediums. Okay. Okay, so now, going along with the slides, let's go over transparent and opaque materials. So of course you probably know what transparent means. Basically means you can see through it. In other words, since you can see through it, that basically means light travels through it. All the light can travel through it. Light travels transparent and opaque. So opaque is basically kind of like the opposite of transparent. Basically just means that some of the light's going to be absorbed by the object. So here some light will be absorbed. Absorbed. So they have a picture of some glass here, and this glass is opaque. It's opaque. And then there's like a little flower over here. right? And we have basically different forms of light coming in. We have the ultraviolet light, high frequency, some visible light, and then we have infrared light, which is heat. So we have all these forms of light here coming in and hitting this basically opaque material. So basically it's going to block out the ultraviolet light and block out the infrared light and only allow the visible light to come in and, you know, make the plant happy. All right, so that's basically the difference between transparent and opaque material. Okay. So now let's compare light to sound, because light and sound are both they're both waves, right? Light and sound are both waves. So we know basically energy can be transferred through a wave. So energy can be transferred through waves. And basically no energy can be transferred through waves, simply just from the whole resonance and the opera singer breaking glass with her voice. So the opera singer sings out, you know, her voice travels in the form of waves. Those waves then hit the glass begins to resonate, and then the glass breaks. And so that's basically her transferring energy to that wine glass, causing it to break. So that's sound, right? So light, since light is also a wave, behaves in that same way. So light can also transfer energy, right? So if you think of, let's say I have two forks here. Tuning fork and another tuning fork over here. If I were to hit this tuning fork so that it vibrates, so now it's vibrating. And so sound, where this is basically the wave front or the waves of the sound, but the sound travels in this direction. All right, so the sound, this thing is going to vibrate, giving off sound waves, right, which are these curved lines. And then the sound waves are going to travel to this other fork, and then this fork is going to absorb those waves and also cause it to shake as well. So then if I were to ring this fork right by this fork will also begin to ring, because it's absorbing some energy from the other fork. Okay, so now let's think about light, because light behaves the same way. So if I have basically some glass here, some thick piece of glass, and I have light coming in, boom. So light comes in, boom, hits this glass material, but this glass material has little atoms inside of it, right? So these atoms are going to absorb that light. So I'm not sure how I'm gonna draw this. Let's draw it like that. It's a little atom there, little atom here, little atom here, little atom here. Boom. So these are the little atoms inside this material. The light then hits this material. The light's gonna travel through it. So in order for the light to travel through this material, these atoms have to absorb and emit this light basically over and over until the light passes through. So inside, light gets absorbed and emitted. So inside of this material, light gets absorbed and emitted by the little atoms. So this is kind of what's happening inside of this material in terms of if we think of light as a particle. So I didn't mention this before, but light is something that we call, well, not something that we call, light basically behaves like a particle and a wave. And so the particle form of light we call a photon. So whenever I say a photon, I basically mean light. But then light can also behave like a wave. So this here, this part, light being absorbed and emitted is kind of describing what's happening inside this material as if light were a particle or a photon. Because we know basically atoms can absorb photons or absorb light and then re-emit it. If we think of light in terms of a wave, then we can just think, well, in terms of a wave, light's going to just travel through this thing, but it's going to travel at a different speed, so it's going to bend, kind of like that. So let's talk more about how light behaves when it goes into a different material. So first of all, when light travels in different materials, the speed of light is going to change. So c, which is the speed of light, we know it's 3 times 10 to the 8. So this is in a vacuum slash air. So light can also travel in other materials like water or glass or diamond. So let's say I'm calling the speed of light in water is equal to 0.75 times c. So notice this c basically is for the original speed of light. So if we take that speed of light and multiply it by 0.75, it's going to be less than what it was. So once light travels in water, it's going to be traveling slower. So speed of light in glass is what was 0.67 c. So light is going to travel even slower in glass. And then they also give us the speed of light in diamond, which is 0.41 c. So in light or in water, light travels at this speed, which is a little bit less than the original. And then it travels the slowest in diamond. So then now let's draw out how that's going to look. Well, before I draw that, let me quickly talk about reflection and refraction. So I think I talked about it in the last video, but just to remind you, we have 2 ways that a wave can bounce off of an object. It can either bounce off the object or pass through the object, right? So when it bounces off, that's called reflection. Reflection, right? So if we have some surface here, and we have light coming in, boom. Let's say this is like a mirror. This is a mirror. So the light's going to get completely reflected. So reflection happens when Boom. And these two angles here are the same. So this angle that the light came in at is going to be the same angle that it bounces off with. And we call this angle the angle of incidence, and this is the angle of reflection. And they're both going to be the same for reflections. And so you can basically imagine when you look at yourself in a mirror, it's basically light coming from your eyes, hitting the mirror, and then basically going back to your eyes, causing you to be able to see your reflection in the mirror. So I haven't got into these different materials yet. We're just talking about reflection. So I'm gonna erase these for now. So now, a little bit more about reflection. So here's our mirror, and I have a person here. Yeah, whatever. So this person is looking at themselves in this mirror. Let's say this person has a distance D away from the mirror, right? So this is the mirror. So we know this person is going to see his reflection over here on this side. Well, how far away is the reflection going to be on this side? Well, it's going to be the same distance D, right? Yeah. So basically, when you look at yourself in the mirror, you see yourself the same distance apart, but on the other side of the mirror. And so then overall, if you're looking at yourself in the mirror, the total distance from you and your reflection, so the total distance is 2D. So that makes sense, right? So now, there's also other kinds of mirrors, not just flat mirrors, right? There's curved mirrors that people use for, any kind of reason. I'm just gonna say, makeup reasons. So let's change this to girl. I don't know, let's give her hair or something. Smaller chin. Boom. Okay. So now, there are special kind of mirrors. Not sure what kind of mirror, I'm not sure what they're called, but they're basically mirrors. When you look at them, you seem to be magnified. So instead of having a flat mirror like that, let's say I have this curved mirror, boom, like this, right? So when I have a curved mirror like this, and you look into that mirror, you're actually gonna see yourself magnified. So boom. Close enough, right? So when you look at we call this a concave mirror. This is a concave mirror because you can kind of think it's kind of caving in towards your face. So this is a concave mirror. A concave mirror. So when you look into a concave mirror, you're going to see yourself or your reflection magnified or even bigger. So you can kind of see more details in your face. And then kind of vice versa, if I were to flip this around the other way, we call this a convex mirror. Vex mirror. So what do you think is going to happen here? All right, well, we're just going to see yourself again, but even smaller. Through a convex mirror. So that's kind of all you need to know about concave and convex mirrors. Just that if you look at a concave mirror, you know, remember it's going to cave in towards you. You're going to see yourself magnified. Versus in a convex mirror, you're going to see a smaller version of yourself. So now that's reflection. So now let's get into refraction. Where again, just to remind you, refraction is when light passes through, or a wave passes through an object and is bent in some direction. So let's use the light and water scenario. So we have some water, boom, and we have some light coming in. Boom. So this light here, you know, is traveling at the speed of light, but then once the light gets into this water, it's traveling at the speed of light in water. So here, it's traveling, I think it was 0.67. Is that what it was? Let me check. 75 times C. Okay. So up here, it's traveling at the speed of light. So 3 times 10 to the 8, or that speed, right? And so then once it passes through this water, the water is gonna bend it because it's now traveling even slower. So the light's gonna bend and travel in this direction. So whenever light is slowed down, so here it's slowed down. So whenever light is slowed down, it's always bends towards the normal. Whenever it's slowed down, bends towards, I spelled that wrong, towards the normal. And so basically the equation that describes what happens here, and basically call this angle up here theta 1, this angle on the bottom theta 2. The equation that governs what happens here is called Snell's law. So again, whenever light is slowed down, it bends towards normal. So here it bends towards the normal, where this dotted line is the normal. So the equation that describes this here is Snell's law, which it says N1 sine theta 1 equals N2 sine theta 2, where theta 1 is the angle the light makes with the normal here. Theta 2 is that bottom angle inside the other material, and N1 and N2 are what we call the index of refractions, where the index of refraction just tells you basically how the light is going to be bent inside of different materials. So let me see if I can describe that a little better. So the index of refraction is basically given by the ratio of speeds. So it's basically the speed of light divided by the speed of light in whatever material it's in. So in air, the index of refraction equals 1. Because you can imagine in air, we know the speed of light is basically this number, just c. So for air, n is c divided by basically c. So we just get 1. And so here, this would be just 1. N2, which should be for the bottom here. So up here is N1. Down here is N2. This part here is going to help you for the lab. So yeah, this bottom area has an index of refraction called N2. N2 is going to be given by c divided by the speed of light in that material. So the speed of light in water, we know, is 0.75 c, right? So these c's cancel out. And we have basically N2 is 1 over 0.75. Let's see what that gives. So that gives us about 1.33. So boom, the index of refraction for water then is given by this value. So that's going to be our N2. So if we know what N1 is, we can basically solve for N2, or vice versa. If we know what N2 is, because we also know what N1, we know what N1 and N2, then we can find theta 1. All right, so let me do like an example with some numbers so that it's a little clearer. So N1 equals 1, N2 equals 1.33, where I got this from dividing those two. And N1 is just basically, the index of refraction in air. It's just 1. So let's say if theta 1 equals 30 degrees, so light is coming in, hitting this water at 30 degrees, where 30 degrees is made with the normal. So not this angle, not that angle, no. This is the angle made with this dotted line with the surface. So that angle is 30 degrees. Then what is theta 2? What's going to be the angle once it goes through the water? Well, using Snell's law, or this equation here, N1 is just 1 sine of 30. Well, we can figure out what that is by just putting it in our calculator. N2 is 1.33. And then we're trying to find this theta 2. Okay. So first, let's do this. Let's find for sine theta 2. It's a different color. So now we know sine theta 2 equals, we're dividing N2 over. We have N1 over N2 sine theta 1, right? Well, N1 is just 1, N2 is 1.33, and theta 1 is 30. So put in all that in the calculator. Let's see. 1 over 1.33 times sine 30. Okay. So then we get 0.3. Let's go 376. That's a 3, 7, and 6. I'm not sure if you can see that, but 3, 7, and 6 is what sine theta 2 is. So now we can solve for theta 2 by taking the arc sine, or the inverse sine. So theta 2 equals And then we just put that in our calculator using the inverse sign, the sign with the -1 or 0.376, and get 22 degrees. So theta 2 equals 22 degrees. Boom. All right, so that makes sense. So theta 2 should have been smaller than 30 because we know it's bent towards the normal. So this angle here should be smaller than that angle, and it's 22 degrees. So all that checks out. So this part here that I'm kind of describing is basically what the lab is going to be going over. So the lab basically has you use Snell's law, and I've kind of basically described to you, for this situation, this is how Snell's law works. But this top medium may not always be air. It could be something else. It could be glass. It can be, it could be anything. And so that's just going to change your index of refraction here. So just take a note of that, and note that these angles here are the angles that's made with the normal. Cool. So I know that was kind of a lot there, but that's all the math I'm going to go over for this lecture here. I may go over one other equation, but this is the bulk of it here. Okay, so moving on in. So we've gone over reflection, refraction, how light bends towards the normal, if it slows down. Okay. Ooh, let me quickly go over the prism. Let's go over the prism. So we've all seen, pictures of some triangle like this that has some light going in, and then it has all kind of colors coming out. And then, all the other colors in between. So red and blue are always going to be the extremes, because the red and blue are on opposite sides of the electromagnetic spectrum, right? Cool. So this here, this light that comes in is called white light. White light. Well, white light basically just means it's a combination of, the whole color spectrum. So this is red, blue, green, purple, yellow, all of those colors are inside of this white light. So then once this white light, which is a mixture of all those colors, goes through this prism, since it goes through this prism, which is in a different medium, this prism could be like diamond or whatever it is, it's going to cause the light to slow down, right? So once the light gets inside of here, it slows down. Now, once the light slows down, since this white light is full of a bunch of different colors or a bunch of different frequencies of light, they all bend a different amount. So notice here, the blue light is going to bend the most because it has the highest frequency, whereas the red light is going to bend the least because it has the longest frequency. Yeah, so blue has a higher frequency than red light. So if you look at page 45 or slide 45, the question says, when white light passes through a prism, green light is bent more than what? Well, green light is not bent more than blue, but green light is bent more than red. So blue and purple are going to be kind of down here, then red and yellow up here. So green light is bent more than the red light. And again, where these different bendings are just happening because for one, light's going through this material, and then once it goes through this material, the different frequencies are bent by a different amount, causing these colors to separate. And then on the other side, we get all of those colors. Okay. So I'm not gonna go over the rainbow just because I think the professor in Mastering Physics goes over the rainbow example pretty well. So I'm just gonna get into polarization, which is the last part of this lecture. Polarization, boom. I know this word is tricky because we have this same word in electricity, but here polarization is a little different. So basically polarization just means the alignment of waves, the alignment of the electric part of the waves and light. Right, so we know light is made up of electric and magnetic waves. So polarization just means when we align light in a certain direction. So if you think about what unpolarized light means, unpolarized means it's just random, chaotic light. So if I have the sun here, the sun gives off light. The sun gives off basically white light, which is unpolarized light. So white light, i.e. white light is unpolarized. Can't spell. Well, white light is unpolarized. So that basically means the light that comes out of the sun is, it's going like this way, that way, that way. It's going all kind of random, crazy ways. This is what we mean by unpolarized light. It has no direction, nothing. So now we have an object called a polarizer, which is basically just some type of film that's going to organize or align this light. So I use a circle for that. So it's up and down. So basically once light passes through this lens, basically, what we call it a polarizer, it's going to polarize the light into a certain direction. So then once the light passes through here, now the light's going to be organized and aligned in the up and down direction. Because none of the other light's going to make it through because it's too random. But the light that's going up and down will be able to pass through this polarizer here. So same thing if the polarizer were in the left and right direction. Kind of like this. Then once the light passes through there, it's going to be going in kind of in that direction. Boom. So unpolarized light, polarized light. So this is polarized. Okay, so now let's imagine that, keeping that idea of polarization in mind, we have this unpolarized light, right? unpolarized. Then we put our polarizer here. So now we have polarized light going up and down that comes out. Let's say I put another polarizer here going this way. Now, how much of the light you think is gonna make it through? Well, before we get to that, let me actually redraw it. Let me do a different scenario. Let's say the polarizer is like this at some angle. Then what's gonna happen? Well, the light's gonna come out on this other side, but it's gonna lose a little bit, right? Because some of it kind of got cut off because of this angle. So now the light's gonna come out a little bit smaller and going at this angle here. So basically, the angle between these two polarizers determines how much light is going to come out at the end. So let me write it like this. Now this way, how much light do you think is going to make it through? Well, here, since the wave is going up and down, or the light is up and down, and the polarizer is right and left, none of the light can pass through that. So it'd be, basically none would pass through. I'm just draw a line for that. So no light would pass through. Okay. So that's polarization, and lastly, polarization only works for transverse waves. Oops. Boom. So polarization only works for transverse waves. So it doesn't work for like sound waves, because sound waves are longitudinal, meaning they go kind of like this, they contract and expand, versus up and down like this, which is a transverse wave. So polarization only works for transverse waves. Okay. Well, I think that's about it for this lecture. I did skip over, some things here and there that you can just kind of read up on. I went over, described the lab and Snell's law a little bit, and just to kind of throw you some equations that you should always remember when talking about waves. The speed of the wave is frequency times the wavelength. If we're talking about light, then it's going to be equal to c. And what else? Oh, frequency equal to 1 over the period t. And there's also one last thing I want to say. I'm not sure if I mentioned it. So when light passes through a different medium, right? Boom, boom. Light travels through a different medium. So here it travels through water. We know it's going to bend towards normal. All right, well, that's theta 1. This is theta 2. So since the light changes speed, so light changes speed. So the speed of light changes, but the wavelength stays the same. The frequency changes, but the wavelength is actually going to stay the same. So light changes speed. So since the light slows down, the frequency is going to decrease. So light changes speed, so it slows down. So it slows down. when the light slows down, the frequency is going to decrease. Wavelength stays the same. Use this wavelength. Stays same. Boom. Not sure if I mentioned that earlier or not, but yeah, so once light goes from this medium to this medium, we know it slows down, right? So since the light slows down, the frequency is going to decrease, but the wavelength is going to stay the same. Okay, so I think that's about it now. Good luck. Got one more lecture and one more test, and that'd be it for the class. Thanks for sticking with me.